This lab deals with an AM voice transmitter. In this lab, we're going to make a transmitter using a negative resistance oscillator. And I'm going to start first by looking at the AC topology of the circuit, and we'll put the biasing later. Here we've got a parallel L and C, and then a capacitor across the base collector, and an inductor across the base emitter. Now the resonant frequency of this LC combination is 1 over 2 pi squared of L2C2, but let's assume that at that frequency that the impedance of the inductor is much less than the impedance looking into the transistor, which I'll just call Z pi. Also I have C3 in parallel with C mu, and that'll be much larger in capacitance than what's here. So these will dominate the AC circuit. Put in the equivalent circuit with those things omitted. So between the collector and emitter we have GMV pi in parallel with R0, and then the R pi and C pi are swamped out by the impedance of L1. The capacitor C3 is swamping out the impedance of C mu. Now let's take a look back into the transistor amplifier from these two terminals with R0, L2, and C2 removed. To find the impedance looking into this part of the circuit, let's apply a test voltage, calculate a test current. So the current coming in here is this current. It can be equal to the current that leaves the node. So this is in terms of V pi. So let's figure out what V pi is. Well, because this current is the same in the two elements, I can use the voltage divider rule. So V pi is equal to SL1 divided by SL1 plus 1 over SC3 times the test voltage across these two terminals. My test then is equal to GMV pi plus the current in this series combination. Here's my GMV pi. And the current in these two elements is just the voltage V test divided by their total impedance, which is SL1 plus 1 over SC3. I can substitute in for V pi from this expression. Both have the same denominator, common denominator, and in the numerator I have GM times SL1. I just have a 1 over here. So now I've got I test in terms of V test. Bring this on this side of the equation and bring this on the other side of the equation, so you get the reciprocal of this as SL1 plus 1 over SC3 divided by 1 plus GM SL1. Let's plug in the fact that we're looking at a single frequency for our oscillator. Place S by j omega L1 minus J over 1 over omega C3, and then 1 plus j omega L1 times GM. Now suppose that at our resonant frequency that this term is smaller than this term. I could throw it away. And that this term is smaller than this term. In other words, omega L1 is much less than 1 over omega C3, and 1 is much less than omega L1 GM. If that's true, then Z out is equal to minus J times 1 over omega C3 divided by j omega L1 GM. Now the J's cancel. You bring this numerator into the denominator, so I get 1 over omega squared L1 C3 GM, but I have a minus sign. And now I've created a negative resistance at a single frequency. Now our Z0 that we just found is in parallel with R0 plus the losses of L2 and C2. Let's take a look at that on the next page. In other words, we found our value of Z0 looking back into the circuit, and then in parallel with that is R0, and then L2 and C2, but they have losses. Represent those as series resistances. We know that we can convert that into a parallel resistance and into a parallel resistance. What I really got here is 3 resistors in parallel, and if I pick the value of Z0 to equal this, then the parallel combination can be the product over the sum, but because Z0 is a negative number, the product would be a negative number but divided by the sum, which would be equal to 0. So that would be approaching infinity. All this disappears at a single frequency, and all you're left with is an L and a C in parallel. That's going to resonate at a single frequency, and that'll produce a low distortion sine wave. Here's my design for the oscillator part of our transmitter. I took this from a hobbyist magazine article. I'm just going to identify the components here. Here's our L1 and L2 and C2, and lastly C3. So at the frequency of oscillation, this will look like a short circuit, and put this value of C3 across the base collector. And when you short circuit this is going to bring this back to ground, and it'll have this inductor then shorted to this point back to ground. We're going to pick the resistors here big enough that we can neglect them, and then likewise over here, I've got my L2. This is again shorted back to ground, so I have L2 in parallel with C2. Now I've added a small resistor here so that I can introduce the amplitude modulation. Let's calculate the resonant frequency of L2 and C2, which is 10 microhenries and 5,000 picofarads, and 1 over 2 pi square root of that is 712 kilohertz. That puts us in the AM radio band. Now at this frequency, let's calculate the impedance of the inductor L1, which would be j omega L1. So 2 pi times 712 kilohertz times 10 microhenries, and you get J 44.7 ohms. For the capacitor C3, minus J over omega C, So 1 over 2 pi, 712K, 470 picofarads. That's a minus J 475.6. For C1, 0.1 microfarad capacitor, at that frequency of 712 kilohertz, it looks like a very, very low impedance. Basically shorting, again, these 2 points together. Using a 3-volt power supply, I did a SPICE simulation and found that the base current was around 27.5 microamps. It can also give a value of R pi of 1K and C pi at 54.4 picofarads. Now the impedance of that is going to be minus J over omega C, so 712K times the 54.4 picofarads. That's a minus J 4.11 k ohms. Again, what's in parallel with that is L1, so it's going to swamp that impedance out. Also, we had some other assumptions to get our negative resistance, and that was that omega L was much, much less than 1 over omega C3. And you can see right here, here's our impedance of L1, here's our impedance of C3, and it's, again, much, much smaller than that one. And also that omega L1 GM was greater than 1. Plug in the values of 2 pi times 712K times the value of L1, which is 10 microhenries, and the value of GM, calculated from the collector current, or from the SPICE simulation, you get 4.18, and that's greater than 1. So all of our assumptions are valid for making this as an oscillator circuit. Let's take a look at next how we're going to do amplitude modulation. Suppose that I introduce a voltage across this 100 ohm resistor that has a DC level and an AC riding on top of it. But this AC is our audio signal, somewhere between 20 hertz and 20 kilohertz. Now the GM of the transistor is roughly equal to I sub C divided by A to F E sub T. Now since the base current is small, the collector current is roughly the same as the emitter current. The current that's flowing in this resistor, which would be this voltage divided by 100 ohms, would be my current DC-wise and then AC-wise, of course divided by A to F E sub T. So we're going to adjust the oscillator by adjusting the value of DC, and we'll get it to start to oscillate at around 712 kilohertz with the numbers we've shown here. And then this audio signal is riding on top of that. What that's going to do is slightly increase and slightly decrease the value of GM. As you recall from 303 lab, the oscillator is very touchy once you adjust it. Drive the oscillator on more as it increases, and then as it decreases, it's going to shut it off. We turn the oscillator on and off with the audio signal. And that's going to create an envelope around our transmitting frequency of, in this case, 712 kilohertz. Your waveform looks something like this. Here's that high frequency oscillator, and riding on top of that is an audio signal. Here's a sketch of our final design. We're going to pick different values of C2 with each lab bench so that we're not transmitting on top of each other. And we're going to transmit a signal from one lab bench to another. Got a pot here that we're going to adjust the biasing so that the circuit oscillates at whatever this L2 C2 value needs to be. Also going to add an antenna about 3 feet long using some banana wires. And then we're going to add the modulator across the 100 ohm resistor. It's going to be a simple circuit from ECE 302 where I'm going to pull the signal off of here, not use a blocking capacitor, but use the DC value and then an AC riding on top, which is here to be the function generator, but will eventually be a microphone feeding your signal in. You may want to take a look at this circuit, analyze it before you come to lab, maybe run a SPICE simulation, but you don't have to turn in anything. The purpose of Lab 9 was to make an AM voice transmitter, and we need an oscillator to do that. We made a negative resistance LC oscillator to oscillate in the AM radio band from 540 kilohertz to 1.7 megahertz. And we coupled in an audio signal by biasing the oscillator circuit such that the transconductance can be varied. This causes the oscillator to partially collapse and restart with the audio signal, creating amplitude modulation. And this is lab number 9.